Welcome back to JEC Sports and Health Summit. This is the last session of the day dedicated to the most exciting startups in the sports and medical fields. You will now discover two innovative startups in the next 30 minutes. Each of them has 10 minutes to present, followed by 5 minutes of Q&A. Please put your questions on the questions tab on the right. You see a chat tab and a questions tab. Please put those in the questions tab because people can upvote those, and we can focus on those that get the most votes. So our first startup to pitch is Arevo from the US, whose motto is to make the world lighter. Arevo enables ultra-strong, lightweight, continuous carbon fiber products on demand. You'll discover a lot of those, but the Superstrata is probably what they've been most famous for, which is the planet's first true unibody 3D printed carbon fiber bicycle. Our speaker is Sonny Vu. Sonny is the president. He's the CEO of Arevo, but before Arevo, he was president and CTO of Connected Devices for Fossil Group, which acquired Misfit, a wearable tech company he founded. He previously founded Elemental Machines for remote process monitoring analytics, Aga Matrix, biosensors for diabetes, and Firespout, natural language processing. He's founder of Alabaster with investments in 30 plus deep tech startups. Previously worked at Microsoft Research in neurolinguistic programming under Kai-Fu Lee, pursued a linguistics PhD at MIT under Noam Chomsky, and studied math at UIUC. Sonny, stage is yours.
Great, thanks for that. And thanks for everyone for coming. So our thesis is fairly straightforward. We automate the production of carbon fiber composite structures, and through our additive manufacturing techniques, 3D printing. So that's the talk in a nutshell. We can be done at this point, but double clicking into what we actually do. The status quo for making parts for industries such as bicycles is it's a long process, 18 months from new product introduction, from design to mold making to actually doing all the steps to actually use the molds, to curing and whatnot, and then post-processing and finishing. It's a long process, and if you want to change anything, it can be pretty complex. All of this, I think everyone here knows. The process ends up producing parts that, in many ways, the shapes are quite simple. You're limited to what you can do with the sheets. The sizes, the shapes, fixed by application. If you want to make rotors one day and then you want to make fins the next day, that's another production line, another set of molds and tools. And strength, mostly XY. Very, this is, we're all talking about composites because we want strength to weight ratio, right? And so that's so you get that, but it's mostly from a two-dimensional perspective is what one gets. And so our promise to the market with our technology is faster printing, faster production, lower cost, and higher quality. Have your cake and eat it too. That's what we can do with our technology. So how do we do this? There are really three enabling pillars for what we do. It's the software. The software enables us to automatically generate designs that engineers might not think of, that humans might not think of, and really come up with designs that optimize the use of the anisotropic properties of the material. The printing technology, the deposition technology that we have is quite unique. It's directed energy deposition technology that enables a very fast material deposition and essentially no cure time. And the robotics, the control of the system to make this work. And we'll see the system at work in just a bit at the end of the talk. Now, double clicking on into each of these pillars. For the deposition tech, we're talking about continuous carbon fiber, so it's a lot stronger than chopped carbon fiber. Arguable how much stronger, but clearly it's better in that regard. Speed because there's effectively no cure period. We can move a lot faster than many other methods, and the quality is great. We're getting less than 1% void content, and so so we were able to meet aerospace requirements. Airbus, they're one of our early investors. They saw what we were able to do, and we were able to make early believers of them. So excited to be able to deliver on quality, which when you look at this under microscopy, it's effectively homogeneous polymer. The process tech, I think, is something that is really what's enabling us to be able to do what we are demonstrating with our first few products. Open atmosphere. So you don't need a box. I mean, we have a box mainly to protect people from the lasers, for operator protection. But this process can be done in open atmosphere. And unlike additive manufacturing for other materials like metal, for example, the thermal management issues, the thermal stress issues on the structures, we just don't have them, and so it's a lot of less complexity when it comes to the fabrication steps. And material independent. We started with PEEK, and we've moved to we're doing nylon. We can do PEC. There's a number of materials that we can handle. And it's largely software parameterized, so we can just I wouldn't say change on the fly, but we can switch out fairly easily. So what does this all enable us to do? It's we can make complex curves, complex shapes. The size is indefinitely scalable. And one of the best features, it's nearly fully isotropic, so we can get z-axis strength that's pretty unparalleled because we can print off plane. It's not just 2.5D layers. So to make a point out of all this, we launched the Superstrata, and this is really our first. The crazy idea was to launch a B2C product and to show what we can do. The idea here was to demonstrate our ability to manufacture for design. That is, to design something that really was different, and then be able to fabricate that and to actually put into production. So not just make it, but make a lot of it, and make it a lot of it at an affordable cost. And you'll notice here that for this bike, there's no seat tube, so it's the design's quite different from what's out there. The whole piece is a unibody carbon fiber frame, and one of the most interesting things about it really is that it can be customized. So there's a bunch of features that you can customize on the bike, but the best part is you enter in the user enters in their physical size, and the frame is actually computed by our algorithms, and each frame is custom printed. The way you buy the bike even is quite different. You actually just go onto our studio, you pick out what you want. There's an e-bike version. The bike and e-bike basically look the same. We just hollow out the inside and put batteries in it for the e-bike. Pick out your colors, pick out the ride style, and voila, there's your bike. We print it, assemble it, and deliver it. Pretty straightforward, really changing the way you buy bikes. We decided to launch this online on a crowdfunding platform just to see how it do. It did pretty well. We were expecting a few $1 million this year. We hit our 3 million mark within 13 days. And so this campaign really just took off, and we just had no idea. We've just been blown away at the consumer interest in this product. Part of it is the tailwind that we're experiencing in this COVID world. A lot of people want to buy bikes, but people really seem to resonate with the Superstrata concept, the design, and what they're getting for it, a customized unibody carbon fiber bike. So this is really our playbook. Is we're demonstrating B2C applications in order to generate inbound B2B interest. So after we launched this, we just had a spectacular amount of inbound interest. Some folks actually thought we're a bike company, which is taking things quite literally, and that's okay. We can print bike frames, but there were quite a few companies who were just interested in us, who said, wow, if you can print that, then you can, maybe you can print this for us, some other structure. And so we've printed, these are examples of some of the things that we've printed in the company. And so really, we've printed golf clubs, hockey sticks, our tennis racket. We've printed a number of those. A bow, no, not this bow, but we printed but basically anything within a 1 cubic meter build volume. That's what we can do. And so that's pretty much it for my presentation. This is actually something we printed. The entire frame here is, and the wheels, but basically everything on this scooter, we actually printed it for the JEC, and we actually shipped it to France, I think, and then we had to ship it back because the event got canceled. But everything here except for the tires, the brake cables, and the smartphone, I think the seats as well, and the LEDs. Everything else is carbon fiber. The wheels, the frame, the fork. And so we had a lot of fun with this. That's pretty much it. So Benjamin, would you mind playing the video? I'd like to just share with you a quick video on what it looks like. All right. Thank you for that. So that's it. That's the our printer at work at maximum speed. At our current generation, we can pump out 1.5 bikes or so a day per machine. We have a pretty large print farm that we're building here in Vietnam. We'll start with 100 systems in place. Each system is about the size of this room that I'm in, so it's a pretty significant facility, and then as well as a post-processing facility. So it's one of the larger, it's kind of probably one of the most ambitious projects that I've ever undertaken, and certainly in Vietnam, there's never been anything like this. So being able to print large, continuous unibody structures at high speed and in large volume. So if you want to make thousands or tens of thousands of pieces, you know who to go to. That's what we can deliver. So that's pretty much it.
Thanks, Sonny. We've got a few questions, and then I've got some, of course.
Great. Yeah.
So we'll bring this one up. So someone would be interested to learn more about your motivation to move from B2B to B2C with the Superstrata. What was that motivation? Yeah,
that's a great question. So when we first presented what we can do, no one really believed us. And so we printed a bike, and they're like, okay, well, can you really make a lot of them? And then there were a lot of questions, a lot of, MOUs, LOIs. And I was like, you know what? We're done with MOUs, LOIs, and proof of concepts and all that silliness. Stop it. We're just going to print 10,000 bikes. And then we're going to send people the 10,001th bike that we print in 1 quarter. And then there's your proof. And so we figured there's no better proof than to actually deliver an end-to-end product, because we can do it. We just got to print it. Assembling the bike, it's not so bad. And so it's really just to demonstrate what we can do, because there's a lot of promises that startups make, and I just feel like the easy way better to show than to tell.
Okay,
but we're not a bike company. We did Superstrata to demonstrate what we can do, not because we really want to start a bike company. But it's not bad. I mean, it's good money, but that's not our focus.
Yeah, I think you might have answered this. What's the production time for one frame? You mentioned doing 2.5 per day or something.
Yeah, over time, the plan is to do about 1.5 to 2 per day with the current generation system. Our next gen system, which we haven't announced yet, coming out next year, will be several times faster.
And that's per machine.
Per machine.
Per station. Yep.
Yeah. There'll be frame, fork, and seat. So we do frame, fork, and seat post. We're not printing the seat or the crank. I mean, there's a number of things we could print, but those pieces we're just going to buy, just easier.
So is there, after you print, I presume there's some sort of machining that still has to occur, as there is with a lot of 3D printing. Secondary operation.
Yeah, there's quite a bit of post processing we have to do
to get to the aerodynamic shapes and so forth that you need.
Just to get the smoothness and the finish, and then you got to paint it, and so there's a fair amount of work. It's not, I mean, you can see from the video that it's pretty rough when it comes out, but it is one unibody piece. It's like, I don't really think too many people have done, first of all, thermoplastic composite bikes, and two, where the entire piece is one piece. A lot of people talk about unibody bikes, and it's not. It's multi-body that's been glued together. So it's very different.
Okay. One more. Any cost comparison? In terms of, I mean, obviously cost has a lot of factors to it.
Yeah.
Yeah.
Well, it's obviously quite profitable so the plan is to build frames at a cost competitive rate compared to the current way of making composite frames for bike makers. I mean, so it just within the bike world, we're significantly more cost competitive. We don't have bladders, molds, and any of that stuff. So you just print it. So
you're talking about doing this in Vietnam, but it reminds me a little bit of Local Motors model, a little bit where they have micro factories around the world to print. Are you thinking about how you have a distributed model?
Oh yeah. So hyperlocal production. That's the whole point of additive manufacturing. That's the whole promise of additive manufacturing, right? Whether you do it in rural Vietnam or Manhattan, the cost should be about the same. So that's our vision, is to be there as well. But for now, we need one place to scale up and kind of get things warmed up. So the first 100, 200 system print farm will probably be here, and then we'll build more elsewhere as needed.
Okay, thank you. I mean, I think we've basically run out of time. There's still more questions coming in, but we'll need to move on. And if you want to go over and to the right and you want to answer some of those questions, you can do that by typing in.
Okay, great.
All right, thank you. All right, we need to move on to our second startup of the day. That is Mecuris, which is based in Munich. Mecuris strives to be the key enabler for digitally manufactured solutions worldwide, empower those professionals to co-create orthotic and prosthetic products and enrich wearers' lives within 24 hours. So I'm pleased to welcome Franziska Glass, Quality Assurance and Verification Lead at Mecuris. She joined Mecuris in 2017 as a student. She studied biomedical engineering at the Technical University of Munich, the TUM, where she got a deep insight in mechanical engineering, special focus on biomechanics and medical devices. Since the beginning, she works as a project testing specialist. During her studies, she co-authored a publication at the International Sports Engineering Association, and her master's thesis was awarded in the ANSYS Hall of Fame, Best in Show, 2019 Startup. At Mecuris, she supervises the quality assurance of hardware products, which includes finite element simulation, ISO test, material testing, and gate lab studies of prostheses and orthoses. Franziska, the floor is yours.
Thank you for the introduction and welcome to everyone. I want to present to you Mecuris. We are a startup, as you heard, based in Munich. And I want to open with the challenge that we are actually facing in the O&P industry, because we see that there are two big streams. So one could be, let's say, the old way, which is a lot of manual design and a lot of handcraft. And even today, a lot of solutions are based on rubber or even wood. But as you can see already, there's problems because this is very time consuming, and also there is no quality standards. There's no CE marks for this medical product possible. But then, on the contrary, you have mass production. So you have standard production lines that are incorporating a lot of metal or composite materials. But it's hard to be super individual for the patient, because you have prefabricated products. You have products you choose from a catalog, but this cannot be individualized to the patient. And just as we heard earlier, our way to go here is mass customization. And I want to present you the process that we want to build up at Mecuris. So for us, it's super important to highlight that we don't want to replace a medical professional. So in the beginning of this process, it would still be a medical professional that is actually at the point of care for the patient. But instead of then taking patient data and go to the workshop to manually manufacture a medical device, this medical professional can take digital data like a 3D scan and upload it to the Mecuris platform. And on this platform, this 3D scan can still be modified. You can do post corrections that would be really painful for the patient on the digital model. And you can also design the medical device based on this digital model of the patient. So now we do have a nice 3D design of the medical aid that I want to have, but we still need to manufacture it. And here we also rely on additive manufacturing that is happening externally. And yeah, also, as we just heard from Sonny, it was like, it's like, can happen in regional hubs. It doesn't need to be just manufactured in one place, but it can happen all around the world as long as it's a certified production line, because we are still in the medical industry here. And in the end, this product will be shipped to the patient or to the medical professional that is then fitting the patient. And still, the product could be post-processed. There can be an assembly happening, and then the product goes as a finished one back to the patient. So I'm talking about all of that, and you might wonder, how is actually the carbon material playing a role in here? So our view on this is that the carbon material from off-the-shelf products, it's very important. It has a high performance, but there's also some disadvantages that we're facing. So it's hard to customize, like fully customize a carbon product that comes from a fixed production line, and it's hard to involve the patient in here because you don't have a lot of possibilities to have different kind of designs in an automated production. So another stream that we are seeing that comes from a lot of users' feedback that we hear is that more and more patients really want to confidently show their medical aids. And this can be an expression of the personality with a fashion statement, as you can see here on the left, from a Paralympic athlete, fitting to the outfit in a gala show. But on the other hand, we are also taking a focus on children. It's important to mention that a lot of times the acceptance for a medical aid and the willingness to learn how to use it is more important than, or a very important factor next to the performance of the product. So we really want to make the children feel like the coolest kid in kindergarten and to have their fully individualized product. And so the solution to all of that could be just not forgetting about the high performance carbon material, but combine it with the additive manufacturing. And this is our way to go. So as you can see here, this is a prosthetic foot. And we do have the main body, which is 3D printed in polymer. And we can have the patient deciding on the color. We can have different patterns. We had a tattoo artist printing a random design of his into the foot. And on the other hand, we have a really nice anatomical shape that is not only based on a rubber cosmetic shell, but really the main body. And combined with it, to give energy return and to really support the gait characteristics, we still incorporate carbon blades. So you can see here, for example, the patient would walk and the heel strikes the ground, you store energy and release it in the end of the gait cycle, which we know already from other prosthetic products. And on top of that, by having different stiffness level of the carbon blade, you can also adapt again to the patient's gait characteristics. And for that, I want to show you a small video. You can see here we are working also a lot with FE simulations, and we are trying to verify and validate that our products with this new material are also complying with the other products that you actually know from the market already. And even with patient feedback from the Gait Lab, as you can see here, we got nice feedback and we got nice rollover curves that are very similar to products that are on the market, or even more adaptable to the individual gait characteristics of the patient. And yeah, this was also, like Dale mentioned earlier, the prize that we won for the ANSYS Hall of Fame. And yeah, with the FE simulation that we are using, our possibility to test a lot of designs that we can have with additive manufacturing is nice. And yeah, as a small outlook that I want to give you, I want to focus also on orthotics. What we do here in Mecuris already is night splints. So this means that it's an orthotic device that is only worn in the night and is not a load-bearing device. And we can actually already, with our process that I showed you earlier, fully manufacture it and deliver it to the medical professional and to the patients. And it's nice because you have a really form-fitting device, but also you have individualization. You see, you have different colors, patterns, and you can have a lot of different design variants here. But if it comes to more performance, so to ground reaction orthotics that are actually worn during the gait cycle, again, we are trying to focus on a hybrid approach, so to have carbon fiber and polymer-based additive manufacturing in combination. And as you can see here, it would be on the posterior side of the leg, a carbon spring, which is a standard component and which is available in different stiffness levels to support the ankle function. It's in combination with form-fitting parts that are actually holding this carbon blade on the leg and giving, again, the freedom to have automated form-fitting devices that are automatically produced in an automatic process. And on the other hand, you have, again, the co-creation factor with the patient that can individualize the design. And yeah, you can customize it also with different velar stripes, for example, or different kind of attachments to the leg. And we see here always this nice combination between the carbon material and the polymer-based additive manufacturing to have hybrid solutions that are really customized to the patient in design and also performance, but we still have the support of the carbon material for the performance and stiffness that we need. And with this, I want to close my presentation, and I'm happy to answer a lot of questions.
Thank you, Franziska. And a very interesting presentation, very interesting company. Was on your website, and obviously people seem to have a lot of fun. Very cleverly designed website, and looks like a fun group, young group. And if I recall, you have somewhere around 30 employees. Is that right?
That's correct. Yeah, somewhere around 30.
Yeah. No, I mean, are they all in the Munich area, or are they located elsewhere on the globe?
I mean, at the moment with the COVID situation, we are, I guess, not everyone in Munich, but our office is only based in Munich. Okay.
All right. Okay. A couple questions. We've got one is who has the responsibility for the product? I think the question with the machine provider, but is that Mecuris, or is it the medical professional at the end? For the performance and any liability.
So that's a kind of tricky question because, of course, we are here in the medical market, and it depends a bit on the product. So the prosthetic foot that I showed you, we deliver it as a finished product. So we are the manufacturer of this medical product. So we also have the responsibility on it. But if you look in the orthotic area, the 3D printed parts are only, like, let's say, part of the assembly of the whole medical device. And in this point, the medical professional is the actual manufacturer of the finished product. So it kind of shifts a bit the regulatory background.
Okay, thanks. Another question, what about the material and its recyclability? As human bodies are changing over time, being able to modify or recycle the orthotics or prosthetics is meaningful. I was going to ask you, what kind of polymers do you use? Are those filled or unfilled? Carbon fiber or glass? And then, are you able to? Are they kind of hard to the touch, or they have soft touch characteristics as well?
So if we are focusing, let's say, on the recyclability, in in the additive manufacturing, you have different base materials. I think if it's based on PA12, for example, this is the sustainability is not as great, but PA11 is based on plant, so it's a nice touch to the sustainability. And can you repeat what's the other question you asked?
Well, it's about the hard touch, soft touch to the touch. Is that what you say with the PA11 gives you the kind of the softer feel?
For sure. We have to, like, usually if you build an orthosis, for example, that has direct contact to the skin, there's some cushion glued into it. So if you have special pressure points, you would try to avoid that. Or you can have also printed patterns that are actually movable and that avoid these pressure points. Okay.
Question about, you talk about the scanning, but if somebody, in a prosthesis has lost part of their limb, there's nothing to scan on that side. Do you scan the opposite side and create a mirror image? Is that the idea there?
So
like scan the left leg if they lost the right, for example?
Yeah. It's a good question. If we think about the prosthetic foot itself, we are based on other parameters like foot length and foot width, and we are kind of scaling a more standard human shape to it. But if we talk about prosthetic covers that we are also doing, which would be a cover that is just replicating the leg and the lower leg, the shape of the lower leg, we would scan the opposite side if it's available and try to replicate it individually to the patient.
Okay, very good. What do you think is the biggest impediment to getting your business model out there? And because one of the things people think 3D printing, obviously if you're a doctor, you're not an expert in 3D printing, but so how do you get doctors to buy into this and use it?
By proving the concept, spreading the word for sure, and also by relying on other industries. So the additive manufacturing method is by far not new to the medical industry. If you look at dental industry, it's very well established. And you have always a lot of examples that you can prove that this method is working. Sure. And these medical professionals working in the O&P industry are very hands-on. So if you give products in their hands and they are convinced by it, they lose the initial fear for it, probably.
Well, I guess by now some of them are fairly used to design tools anyway. So, because even in the manual processes that they've done in the past. Okay.
Sure.
Yeah. You're obviously an FEA expert, having won an award there. Is that sufficient to reduce the development time, or do you still need a lot of, trials and failure analysis?
I mean, of course, the simulation part could never replace the final validation with the patient, but still, usually we parameterize our products and we have a large design space. We have really many design variants, and regarding the safety of the product, so for the medical area, it's very important. We would only actually test on a physical test bench the worst case of it, and all the other design variants we can argue with the simulation. And so this is a very fast process to actually bring a medical product to the market. Okay, all right. We've reached the end of our time, and we're very cognizant that it's almost dinner time in Central Europe right now, and for Sunny it's bedtime because it's after midnight there in Vietnam. So we appreciate both of your participation today. Very, very interesting products. And we also appreciate the sponsorship of Supreme, our main sponsor of today's events. And don't forget that the workshop continues the next 2 days. You should, if you've registered, you received invitations for each of the next 2 days. Thank you, Benjamin and the JEC team for putting on this event. And that will close today's activities. Thank you very much. Thanks, Sunny. Thanks, Francisca.
Thanks for having us.
Thank you all.